All right, let's be honest. Have you ever seen a symbol like this and thought, what in the world is that? Well, this is a radical, and it's actually one of the most powerful tools in all of mathematics. And it's not just for weird abstract equations, it helps us solve real-world problems. So today, we're going to crack the code and break it all down. Let's kick things off with a very practical puzzle.
Imagine this. You need a ladder to get to a window that's 12 feet off the ground. Simple enough, right? But here's the catch. For safety, you have to place the bottom of the ladder 5 feet away from the wall. So the question is, what's the exact length of the ladder you need? This is a classic little geometry problem, and it's going to lead us straight to the heart of what radicals are all about.
You probably remember this one from school. The ground, the wall, and the ladder form a perfect right triangle. That means we can whip out the good old Pythagorean Theorem. A squared plus b squared equals c squared. So we've got 5 squared plus 12 squared equals our ladder's length squared. That's just 25 plus 144, which means 169 equals c squared. And that leaves us with this big question. We know how to square a number, but how do we do the opposite? How do we unsquare 169? Well, that is the exact job a radical was invented to do. We're looking for what's called the square root. Okay, so before we figure out the ladder situation, let's just hit pause and make sure we all understand the tool we're about to use. So, first things first, what exactly is a radical?
Let's break down the anatomy of this thing. This whole expression is called a radical expression. That checkmark symbol, that's the radical. The number under the symbol, in this case our 169, that has a fancy name, the radicand. And sometimes you'll see a tiny little number tucked right into the corner there. That's the index, and it tells us what kind of root to take. Now, if you don't see an index, like in our ladder problem, it's automatically assumed to be a 2 for a square root.
All right, let's tackle a super common question right now, because this trips a lot of people up. We all know that 5 times 5 is 25. But hey, -5 times -5 is also 25. So does that mean the square root of 25 is both positive and -5? And the answer, which might surprise you, is no. By a long-standing rule in mathematics, that radical symbol is defined to mean the principal root, which is just the positive one. This is so important because it means our answers are always consistent. So if you see the square root of 25, the one and only answer is 5. It's a rule we all agree on to keep the math working smoothly. Awesome. Now that we know what these things are, let's start building up our toolkit. There are a couple of really key rules that let us take messy radicals and simplify them, which makes everything way easier to work with. So here are our 2 secret weapons, the product rule and the quotient rule, and they are incredibly powerful. They basically let us do one of 2 things. We can either break down a big, nasty radical into smaller, friendlier pieces, or we can combine a bunch of separate pieces into one. Let me show you what I mean. Let's use that product rule on the square root of 300. Now, the main strategy here is to hunt for the biggest perfect square you can find that divides into 300, and in this case, it's 100. So we can rewrite 300 as 100 times 3. Now, thanks to the product rule, we can split that into 2 separate radicals, the square root of 100 times the square root of 3. We know the square root of 100 is just 10, so our final simplified answer is 10 root 3. Much cleaner.
Okay, so we can simplify radicals. That's cool. But can we do basic math with them, like adding and subtracting? The answer is yes, but there's a catch. They have to be alike.
And here it is, the golden rule. You can only add or subtract like radicals. You know, it's the exact same idea as in basic algebra. You can add 2x and 3x to get 5x because they're like terms. But you can't add 2x and 3y. It's the same here. For radicals to be like, they have to have the exact same number under the root, the same radicand, and the same index.
So if you look at this problem, it seems like we're stuck. We can't add them because we have a 12 and a 3 under the radicals. But wait, this is where our simplifying skill comes into play. We can simplify the square root of 12. We can rewrite 12 as 4 times 3. The square root of 4 is 2, so that first term becomes 5 times 2 times the square root of 3. In other words, 10 root 3. And now look, both terms have a square root of 3. They are now like radicals. So we just add the numbers out front, the coefficients. 10 plus 2 is 12, and our final answer is 12 root 3. All right, next up, we have a technique that sounds really fancy, but it's basically just about mathematical tidiness. It's called rationalizing the denominator, and it's the standard, polished way to write our final answers. So you might be wondering, why?
Who cares if there's a radical in the bottom of a fraction? And that's a great question. Believe it or not, this is a leftover from the old days. Before calculators, trying to divide by a long, messy decimal, like the square root of 2, was a total nightmare. Now, even though we have calculators, the habit stuck around. It's kind of like mathematical etiquette. A rationalized answer is just considered the proper final form.
Now, when the denominator is a bit more complicated with two terms, we need a special tool. It's called the conjugate. All you do is take the expression and just flip the sign in the middle. And here's the real magic. When you multiply something by its conjugate, the radicals just, poof, they vanish.
Let's see this magic trick in action. We've got 4 divided by 1 plus the square root of 5. The conjugate of the bottom is 1 minus the square root of 5. So we multiply the top times and the bottom by that. Now watch the denominator. 1 times 1 is 1. The outer and inner terms, negative root 5 and positive root 5, cancel each other out completely. That's the trick. And the last terms give us minus 5. So the new denominator is just 1 minus 5, which is negative 4. The radical is totally gone. We do a little simplifying and we get our beautiful final answer.
So far, we've pretty much lived in the world of square roots. But this whole system works for any root you can possibly imagine. So let's expand our horizons a bit.
We can have cube roots, right? They just ask what number multiplied by itself 3 times gives you the radicand. So the cube root of 8 is 2, because 2 times 2 times 2 is 8. And this goes on forever. 4th roots, 5th roots, any nth root you want. The little index number just tells you how many times to multiply.
And this leads us to one of the coolest, most beautiful connections in algebra. It turns out that every radical is just a fraction in disguise, specifically a fractional exponent. The rule couldn't be simpler. The index of the root becomes the bottom, the denominator, and the power becomes the top, the numerator. A good way to remember it, roots grow in the ground, so they go on the bottom. These two ways of writing things mean the exact same thing.
Check out how powerful this is. You see something like 343 to the power of 2/3, and it looks terrifying. But don't panic, just translate it. The fraction 2/3 tells us to do two things. Take the cube root and then square the result. Well, the cube root of 343 is 7, and 7 squared is 49. See? Switching forms made a really scary problem totally simple.
So let's tie this all together. Radicals and their secret identity, rational exponents, they're not just random symbols a mathematician made up to be difficult. They are quite literally the undo button for exponents. They are the tool we use to answer the question, what number do I start with to get this result? So let's go all the way back to our ladder. We were stuck at c squared equals 169. We needed the square root of 169. And now we know with 100% certainty that the answer is 13. You need a 13-foot ladder. A simple, practical question unlocked this entire powerful world. What we've done here is build a toolkit for solving a whole new class of problems. The only question left is what are you going to go solve next?